Okay, so we're looking at the second year Stats and Mechanics textbook, and we are doing exercise 4D. So chapter 4 is on moments, and exercise 4D is on the centre of mass. So we've got a problem solving question, so we're going to have to think carefully about our method. We've got a non-uniform rod, so it's that bit that tells me that the centre of mass is not at the centre of the rod. So I don't currently know where the centre of mass is working. So the rod is 5 meters long. I'm given its mass, and this time around it's suspended from 2 strings. So up until this point, the previous 3 questions, the rods were all balanced on pivots. So let's get a sketch of what happens when it's suspended from strings, because it doesn't really make any difference. Okay, so I've got the rod AB, and it's suspended from 1 string at C, which is 1 meter away from A. So there's C. And then it's also suspended at D, which is 3.5 meters away from A. So not drawn to scale. So the only difference is, rather than being reaction forces at those 2 points, there's tension in those strings. Okay, so they're the forces that are holding it up. Okay, and then I am told where the centre of mass is. So the centre of mass is at E, which is 3 meters. So not quite as far. I'll get rid of that, there we go. Okay, so the centre of mass is at E, and the centre of mass is the mass is 15 kilograms, so that's a weight of 15 g. Okay, so they're the only forces. So the actual mass of the plank or the rod, and then the 2 tensions holding it up. Okay, so and I know if I resolve vertically. So it's suspended stationary, so it's not moving up or down. So the downward force of 15 g must equal the upward force, which is the tension at C, plus the tension at D. If you get fed up with writing subscripts, you could always just call those 2 tensions just completely different letters. Okay, so and they want me to find the magnitude. So this whole setup is not symmetrical, so I can't just halve the 15 g and say they're each 7.5 g, unfortunately. So I'm going to have to take moments. So I've got all the distances I need. Let's try and label them on as neatly as I can. So that was 1 meter away from A. Centre of mass was 3 meters. And let's just get D up there. And the string D was 3.5 meters. Okay. And there's no force at B, so I don't need to worry about the distance to B, although I am given that. Okay, so I've got a few options. I could take moments about A. And if I take moments about A, I'm going to have an equation that involves the tension at C and the tension at D. So I'll have 2 unknowns, but then I've got a second equation with 2 unknowns. So that would absolutely work. I'm going to do it slightly differently to the previous ones, though, and you'll see why. I'm going to take moments about C. Okay, and it doesn't matter. You might, if you have a look through the textbook exercises, try a few other questions, you might prefer to take moments about A, but I'll just show you why I'm taking moments about C. So if I take moments about C, I don't have to worry about the force at C, because moments of force times perpendicular distance. So the distance between C and this force here is, and the tension is 0. So I don't have to worry about that force. So if I'm taking moments about C, the only forces trying to turn the plank are going to be that force trying to turn it clockwise. So the moment due to that force is going to be the force of 15 g times its moment. And I just need to be careful. I'm doing distances from C. So it's not tricky. You just got to make sure you're on the ball with this. So the total distance from A was 3 meters. That's 1 meter. So that's going to be 2 meters. Okay. And so that's the only clockwise moment. The only anti-clockwise moment is going to be due to the tension at D. So the tension at D is what I don't know. That's what I'm trying to find. And D is 2.5 meters from C. Yeah, because So that whole thing, that whole length is 3.5 meters, but that's 1 meter. So that distance there is 2.5. Okay. Right, so that means I can get the tension at D straight off just from this equation. So 30G is 2.5 times the tension at D. So 30 times 9.8 divided by 2.5, gives me 117.6. So if I'm going to round that to three significant figures, 118 newtons. Okay, then I can go to this equation and just say, well, therefore the tension at C is going to be 15G minus 118 newtons. So 15 minus the previous answer, so 29.4 newtons. Oh, sorry, no, 29.4 newtons. Okay. So like I said, there's alternatives to that. So if you started taking moments about A, that's absolutely fine. You will end up with the tension at C and the tension at D once you've taken moments about A, but you'll be able to solve those equations simultaneously. So it does work. Okay, so let's have a look at B. Right, I'm going to sketch out again because my sketch it's got a little messy there. So I'm going to sketch it out again. Right, so I've got the rod. I have got a string at C, a string at D. And I've got the weight of the rod at E. Okay, so what they're now introducing is a particle of mass 9 kilograms attached to F, and they're not telling me where F is. Okay, so that shouldn't be a problem. So what have I got? I've got the tension at C, I've got the tension at D, I've got the weight of the rod, which was 15G. Now, these two previous answers are no longer going to be relevant because adding this 9 kilogram mass on has completely changed the tensions. So I can't use those previous answers at all. But what it does tell me is that the tension at D is twice the tension at C. So what that means is I can actually simplify these tensions quite a lot because I no longer need to have two different tensions. I can say that the tension at D is twice the tension at C, and in fact, seeing as they're the same, I can get rid of the subscripts as well, which just makes it look a little bit nicer. Okay, so all that is using this information here, that the tension at D is twice the tension at C. Right, okay, so in terms of where F actually is, so is it between A and C, between C and E? They've not told us that. The fact that, so currently, before they added the 9 kilogram mass, the tension at D was more than twice the tension at C. So that's telling me that this mass F is probably attached closer to C than to D. Okay, but it doesn't matter. So if you had this in the wrong place, it would be absolutely fine. But I'm going to say it's about there. Okay, and they want me to find the distance AF. All right, so what can I do there? Well, always, before I worry about moments, it's always worth just resolving forces vertically, because that's easier, basically. So the total upward force is T plus 2T, and the total downward force is 9G plus 15G. So 3T is 24G, so T is 8G. Okay, so that's going to be worth some marks. It's just a lot easier than taking moments. So the tension at C is 8G, and the tension at D is twice that, so 16G. All right, okay, so now I need to think about where to take moments. So I'm trying to find this distance here. Okay, and I have got a few options. I could take moments about A. That's what I might do. I don't know if that's necessarily the quickest way, but I think it might be the most obvious way. So I could take moments about A. because I've got 4 forces to worry about, the 8G, the 16G, the 9G, and the 15G, but I know all of the distances apart from X, and that's the one I'm trying to find. You might also, though, want to take moments about C, because if you take moments about C, then you don't have to worry about the 8G force. Ditto, well, maybe not F, but if you took moments about E, you wouldn't have to worry about the 15G force. So there's certainly arguments for taking moments about C, E, or D, but I think I'm going to stick to A, just I think that's probably the most obvious way to tackle this. Okay, so I'm taking moments about A. I have got, so let's label on all these other distances that we were given. Let's use blue. Okay, so this is all from the original question. I was told that that was 1 meter. I was told that that was 3 meters. And I was told that that was 3.5. Okay, so that was all given to me in the original question. Right, so what moments have I got? Well, I've got these two. So if I'm taking moments about A, I imagine I've got like it's pivoted at A. So those 2 forces are both going to be trying to turn that clockwise. Yeah, so literally imagine it's the hand of a clock. That's the center of the clock. F and E are going to be sort of pulling downwards, so trying to turn it clockwise. So the moment due to F is the force of 9G times the distance of X. Yeah, I don't know that distance. That's what I'm trying to find. The moment due to at E is going to be the force of 15G times the distance of 3. Okay, so they're the 2 clockwise moments. There's also 2 anti-clockwise moments. So again, imagine we sort of pivoted there. Both of these are going to be trying to turn it anti-clockwise. So I have got the 8G, and that's 1 meter away from A. So that's just 8G times 1. And then I've got the 16G, and that is 3.5 meters away. So just about squeeze that on. Okay, so let's just tidy all that up. So I've got 9GX plus 45G is 8G plus 56G. So 9GX is 8 plus 56 minus 45 is 19G. So X is 19G over 9G. So 19 divided by 9 is 2.11 meters. So it actually turns out, let's put that one on one page. So it does turn out that, RF was roughly in the right position. Yeah, so that was 3 meters to E, it was 1 meter to C. So if F is 2.11 meters, it's in roughly the right place. But if it hadn't have been, it really wouldn't have mattered. So if this has ended up being 0.9 meters, it would have meant that F was there, but it wouldn't have changed any of my calculations. So let's just quickly check those answers. Yeah, we're good.